we will denote the ideal by I. We will denote the ideal E by I. Okay. So we have to prove that if I is not subset of Pi for any I, for all I, then I cannot be inside the union, right? I mean, we are proving the contrapositive statement, right? So we will proceed by induction on N. So if N equal to 1, we are done. Suppose the statement is true for 1 less than equals to k less than equals to n minus 1. We consider P2 to Pn, and we have I is not a subset of Pi for 2 less than equals to I less than equals to, since P is not inside I for any I, okay. So in particular, I is not inside Pi for I 2 to n. So then, by induction hypothesis, I is not inside the union. I is not inside union. Then there exists xi belongs to I such that xi is not inside union Pi, I running from 2 to n. I mean, what I am trying to say is that, so there exists xi belongs to I such that xi is in I, and I mean, we should be writing like this: xi is not in Pi, right? Because I mean, each element in I has to skip at least some Pi, otherwise I will be contained in the union. So there exists xi such that xi is in I and not in Pi. Sorry, it's not in Pi. So if x1 is in P1, so if x1 is not in uh, P1, x1 is not in P1, then x1 I mean if x1, wait a minute, if x1, we are done, and we are done. So without loss of generality, let so x1 is not in P1 and not in the union. If x1 is not in P1, but just a minute, this may happen that x1 is not in P1, but I will pick another x1. So I mean we should be writing like this. If for every x belongs to I, x belongs to union this or union or x belongs to P1, then I mean there exists an x which is not in P1, right? I mean we need to take that. Just a minute. What is our induction hypothesis? We are trying to show that if I is not in Pi, just a minute. I'm a bit lost here. Give me a minute. there exists x1 such that x1 belongs to p1 Why should that happen? Because basically so you choose one x1 belongs to I, huh? So x1 cannot be in all the PIs. I mean x1 is not in the union, right? So you take P1, I is not in P1, so there exists x1 such that x1 is not in P1. Wait a minute. This prime avoidance. This is a weird approach they are taking. Just a minute, just a minute. Why the hell is it doing so? Just give me a minute. Just give me a minute, just a minute. Wait a minute. I have a stronger statement. Just a minute. This is the statement. Finally. This is a stronger statement. Just a second. Just a minute. This is a stronger version. Let R be a COM ring with unity. I1 to In and J be ideals in R such that at least n minus 2 of the ij's are prime and J subset of I1 In. Then J subset of Ij for some. So I hope you understand that this is a clear, this is a stronger statement, because in the above statement they have taken all the prime ideals. But in the latter statement, we are relaxing the above condition a bit. Like at most two of them can be non-prime. Okay. So proof. By induction, of course. So for n equals to 1, it is obvious. So for n equals to 2, so suppose J is contained in I1 union I2. Okay. If possible, let J is not contained in I1 and J is not contained in I2. So there exists x1 belongs to I minus J minus I1 and x2 belongs to J minus I2. Now x1 plus x2, this belongs to J, right? But x1 plus x2 is not in I1. Why? Because x1 is not in I1. But if x1 plus x2 belongs to I1, then so x2 is not in I2, right? So if x1 plus x2 is in I1, then what happens? Then x1 plus x2 minus x2 belongs to I1, which is a contradiction because x1 was not in I1. But why should x2 belongs to I1? Okay, so see, if x2 is in J, then x2 is in the union and x2 can't be in I2, so x2 is in Y1, okay, which implies x2 is in I1 and this implies x1 is in I2, right? Because x1 is in J and not in I1, but x1, because J is contained in the union, right? So similarly, I mean x2 equals to x1 plus x2 minus x1, this belongs to I2, which is a contradiction again. Okay, so x1 plus x2 is not in I1 or I2, hence it is not in I1 union into so J is not contained in I1 union I2, which is a contradiction. Okay, now we will use this idea for n greater than equals to 3 without loss of generality. J is not contained in I1 union I hat. Okay, see, we can take the union to be minimal. Okay, the union can be taken to be smallest. By that I mean that J is in the union of n ideals and J is not contained in any union of n minus 1 ideals in them. Okay, that basically we say that J intersects all the ideals. If J doesn't intersect some ideal, just remove it from the collection. Okay, so without loss of generality we can take the collection to be the smallest. So now I mean this is where n minus 2 primes will be used. This is where n minus 2 primes will be used. So take I1 to be prime. Okay, because if you observe in for n equal to 1 or 2, we did not need the I1 or I2 to be prime. Take I1 to be prime. Okay, so for since J is not in this, therefore each I there exists xi belongs to J minus I1. Yeah, that was the step written there, which I was struggling to understand. But this invariably means xi is in I, right? Because xi is in J, so xi is in the union. So xi is in union II for I running from 1 to n. Okay. But we are seeing that xi is not in the union which skips the ith ideal. Hence xi has to be in the ith ideal. So now you consider this. Consider this element. X equals to x1 plus x2 up to this product. Okay. Now see, this is in J, right? This is in J, huh? Because each of the element are in J. Now, claim X is not belongs to Ij for any J. For any J. If X equals to I1, then if X is in I1, then X1 was already in I1, then X minus X1 equals to X2 minus Xn belongs to I1, right? Because now see, I1 is prime, so which implies some xi belongs to I1 where I is in this sum, which is a contradiction, right? Because x2 is not in I1. I mean, if you look at here, xi is in only I, right? Xi, each xi is only in the one ideal, that is the ith ideal. So x2 doesn't belong to I1, x3 doesn't belong to I1, and so on. So the product cannot be there because I1 is a prime ideal. and if x belongs to ij for some j greater than equals to 2, then it implies x2 dot 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 xn belongs to ij as xj is in ij, which implies x minus x2 to xn, this product, equals to x1, this is in ij, which is again a contradiction because x1 is in i1 only. Okay, thus x1 is not in the union because x1 is not in any of them, right? Which implies j is not contained in the union, right? Which is a contradiction. So this is a very important lemma. This is called prime avoidance. So see, we have proven a stronger statement, huh? Okay, so if R2S be an epimorphism of rings with kernel K, P is prime ideal in R that contains K, then if P is a prime ideal in S, Q is prime in S, F inverse Q is prime in R that contains K. There is one-to-one correspondence between the set of all prime ideals. Okay, this is also known as the correspondence theorem. Okay. Piash is here, na? পিয়াস তো রিং থিওরি পড়া আছে?
হ্যাঁ পড়া আছে, এবারে ফোর্থ সেমিস্টারে আছে তো ওই জন্য।
Very good. I hope this will help because there is no better book than Hunger Food.
ঠিক আছে।
Okay, so P is prime in R contains K, then FP is a prime ideal in S. So K contains P where P is prime. So suppose, and in our discussion, I mean, we are taking commutative rings with identity. Okay, so if xy is in fp, f is an epimorphism, right? So there exists x prime y prime belongs to R such that if x prime equals to x, if y prime equals to y, which implies I mean fp, so I should be writing like p. So this implies that if x prime comma fy prime belongs to fp. Hmm. Just a minute. So can we see that x prime y prime in P? Just a minute. See exercise 13. What was done in 13? Ideal containing car S. Okay. So that so if inverse of if P need not be P, right? If inverse of if P need not be P, right? Mm, I mean, I can use other ways, but I'm just trying to check is elementary in an elementary way because R mod P is an integral domain, so I mean S mod FP will be an integral domain too. But I don't want to go there actually. Otherwise, this is a direct check. If P is a prime ideal in SPS, okay, so let's try to do this. I mean, so P is a primordial. Okay, do you know this thing? I mean, do you know this? That if R to S is a ring homomorphism, then there is a morphism from. Then, do you know this? I mean, by first ring isomorphism theorem, that R mod K, I mean this is a surjective map, so R mod K is isomorphic to S. The first ring homomorphism theorem. Okay. Now you see what I do. So quotienting out this side, since this is a bijection, R mod K quotiented out by P mod K, because P is an ideal contained in K, we can do P mod K, is isomorphic to S mod F tilde P mod K, right? Right? Because this is a bijection, but what is this? This is R mod P. This is isomorphic to S mod Fp. Now see, what I try to say is that F mod Pk is nothing but Fp. Okay. Because what is F tilde? What is F tilde? Okay. So F here, and suppose we write is pi. So pi of R is, this diagram commutes. So pi of R is R plus K, huh? And what is F tilde of R plus K? That is Fr. So you get this. Since R mod P is an integral domain, because P is a prime ideal, this is also an integral domain. So Fp is prime. Okay. Now for B, if Q is a prime ideal in S, then F inverse Q is a prime ideal in R that contains K. Now this is comparatively easier. See, 0 belongs to S, which implies, 0 belongs to, what was the notation by the way? Rejwan, if you can't understand something, please let me know. Okay. Is he here? Yeah, Rejwan is here. Okay. And for the primeness, you can just do this. Let xy belongs to F inverse Q. Okay. So they are trying to say that, see, what did we do? For a prime ideal in the domain, we have associated a prime ideal in the codomain. And for a prime ideal in the codomain, we have associated a prime ideal in the domain. So what have we done? If R is in this side and S is in this side, F is an epimorphism. We have sent F to Fp, and we have shown that this is prime implies this is prime. Similarly at this, we have shown that if Q is prime, F inverse Q is prime. Okay. But is this correspondence one to one? That should be a natural question. Like, can it happen that, can it happen that uh, if P equals to FQ, okay, so what can we say? So let PQ prime in R and FQ equals to FQ, okay, but these are also prime, right? Prime in S, you apply F inverse, these are prime in R. No, it is enough to show that actually this is enough to show. So for C, it is enough to show F inverse FQ is basically Q. That's enough. Not for Q. Maybe I should be writing like P. Okay. Then this becomes a one-to-one bijection, right? Then this becomes a one-to-one correspondence, right? So how do we do it? And we have this, R mod P is bijective to S mod FP. We already have it, okay? Right? Now let's look at this map carefully. Not exactly F tilde. You have to understand this map a bit carefully. Like, take this diagram. Maybe call it G. Okay. So what is the map? R goes to R mod P. Okay. For some reason, I am getting stuck in every problem today. Okay. And we have shown this bijection in 2. So you have to show this, right? That F inverse FP is P. So it's like F inverse Fp. Okay. But what is Fp? What is Fp? This is theta inverse of 0. So it is F inverse theta inverse of 0 here, huh? 0 plus Fp. What is F inverse compose theta inverse? That is theta compose F whole inverse plus 0 plus Fp, right? And theta compose F was, call it G. Actually, we don't need to do much thing actually, because you see, since this is a bijection, I mean, this is direct actually. See here, I mean, since isomorphism, I mean, pre-image of no, I was doing that correctly. What the hell I am doing? F inverse Fp, which is like F inverse theta inverse 0 plus Fp, which is 0 here, which is theta compose F inverse 0 plus Fp. Okay, so what is theta compose F? That is G compose pi. So G compose pi of pi inverse of Fp. This is pi inverse compose G inverse of 0 plus Fp. Now see, G is the isomorphism, right? G is the isomorphism. So inverse image of 0 is only 0, right? That is pi inverse P. That is P. Okay. Now it is okay because of the commutativity of the diagram. Okay. This is where the isomorphism is used. That G inverse of 0 is only, I mean, I should write this 0 plus P. Huh? Which is P. So this is a bijection, one-to-one correspondence. If I is an ideal in ring I, then every prime ideal of R mod I is of the form P mod I. Okay. So for D, take S equals to R mod I. Huh? Then you have if Q is prime in R mod I mean, maybe I should write like this. If Q is in R mod I, then pi is the map from R to R mod I, or maybe like the previous notation F. Then F inverse Q mod I, which is Q, is prime in R by C. Okay. So this is also called the correspondence theorem. Let's do 18. Okay, you can try 18 for a few minutes. Okay, then see what we can do. So an ideal M mod A ring R in is in a commutative ring R with identity as maximal if and only for every R belongs to this. So we have proved this in the first class, that a commutative ring R with unity. Rizwan, have you seen this video? Is simple if and only if R is a field. Okay, I have done this. So it is a field if and only if R is simple. Simple means R has no proper ideal. Now for if M is a maximal ideal, then R mod M has no proper ideal. Otherwise, if I mod M is an ideal in R mod M, then M subset of I subset of R, right? Which is a contradiction because M is maximal. Conversely, if R mod M is a field, it implies by this R mod M is simple, which implies there exists no proper ideal containing M, which implies M is maximal. So we have basically established that M is maximal simple is a field, right? M is maximal if and only if R mod M is a field, right? Right? So we have established this. Now, for this problem, let R belongs to R minus M. So R plus M in R mod M has a unit, right? Because R mod M is a field. It implies there exists X mod M such that R plus M is equal to 1 plus M, which is Rx, mod M is equal to 1 plus M. Again, if for R belongs to R mod M, there exists X belongs to R mod M, I think. There is x belongs to R such that Rx minus 1 belongs to M, then Rx plus M is 1 mod M in R mod M, right? Which means R plus M is a unit, which implies R mod M is a field. Okay. Okay, I will have to complete my packing, so I will conclude today's class here. The classes have been a bit shorter in span for the last few months. For the last 1 month. I know that. Mainly because of the low attendance. So I did not want to cover much because I did not want you guys to actually miss much. But from from the next week or maybe next to next week, we will try to normalize things. Okay. Because I will have to complete the inner products based syllabus inside February anyway. So that's the thing. Okay, so that's it for today.